Hello, everyone, and welcome to our physics project over the thin film interference. So here are some definitions we have. In thin film interference, two reflections overlap and interfere. It occurs when light waves reflect off two surfaces that are at a distance. When light waves reflect off the top and the bottom surfaces, they interfere with one another, creating a colored pattern. And here we have two examples of that. If you see directly below, the A and B reflect, and you can see the C is creating a different reflection, um, and it's creating a color pattern. So someone to be recognized is Robert Hooke. He was a prominent English physicist, studied diffraction effects and thin film interference. Iridescence in peacock feathers were caused by thin alternating uh, layers of plate and air. So here's the video that we did over the thin film interference of a candle. You can see the two reflections in the window. All right. So as you see in the video, the reflected light waves are causing an interference, which means the light wave being partially transmitted is also being partially reflected, creating the double reflection seen in the reflective surface of the window. The candle is used in order to visibly show how the wave is changing. Light waves are partially reflected from any boundary between two transparent medias, meaning the light is reflected from not only the front of the surface, but also from the back, ultimately creating two reflections of the candlestick. The reflected and transmitted light waves also will overlap and create the interference. So here are some of the equations that we used in the video. So we have the constructed path length difference equation. So difference equals to 2 times the thickness. Since the wave is traveling twice through the reflective surface, this creates a double path length difference. Also, the path length difference is extra distance created from the second reflected surface. In order for the path length difference to be constructive, there has to be 0 or 2 reflective changes. So here we have the destructive path length differences equation. It's the difference is equal to the integer plus a half of the wavelength. In order for the path length difference to be destructive, there has to be only one reflective phase change. And that concludes our video. Thank you so much for watching, and I hope you enjoyed.